Hello, good evening from Nigeria. My name is Ololi Godwin and welcome back to Emoji Economics. We've been talking about derivation, differentiation in our previous classes. Although I mentioned in the last class we were talking about using different rules, combination of rules to solve, like, to differentiate functions. So there are functions that we'll be using one or two, rules of differentiation to differentiate them. And in that last class, I think I was saying that there wouldn't, I don't know if I don't recall if I said there wouldn't be a class on that kind of differentiation anymore. But with the way things are going, there's going to be a class on that kind of differentiation again, because I got to come across some wonderful questions that I would like us to play with in one of our videos. But in this particular one, we shall be talking about something slightly different, which is uses of derivatives in mathematical economics. Now, we've been differentiating in the previous maybe 4-5 classes on differentiation and on calculus basically. But why do we need them? Okay, we should have left calculus to the mathematicians, those in the physics department. But why is it that economics also makes use of differentiation, calculus, and all of that? So now there are 4 basic reasons. There could be more, I don't know, but there are 4 reasons on the board why why mathematical economics, why we make use of derivatives, why we make use of calculus in mathematical economics. So let me just say derivatives. So there are 4 reasons why we make use of derivatives in mathematical economics. So there are 4 reasons why this concerns us. Now, the first is increasing and decreasing functions. For us to know the increasing and decreasing functions. Now, what are increasing functions? Now, in order to know what increasing functions are, so increasing functions are functions that when you draw their curve, tangential to a line, from left to right, that curve increases, that curve rises. So that is an example of an increasing function. This is an increasing function. So this is the curve. When you draw curve A, let's say this is curve A, tangential to a line, which is curve B, from left to right, and the curve increases. As you are, and the curve increases. This is like a point, followed by a point. Let's say you are plotting a graph, followed by another point, so all these points are, they are higher. The subsequent point is greater, is greater than the preceding point. So this point is greater than this, greater than this. So you have a line that is tangential to the entire curve. So when you have the entire curve that is tangential to a line, and the curve is increasing from left to right, from this side to this side, we call that an increasing function. Now, does this qualify as an increasing function? This does not qualify as an increasing function, because though it is rising, though after plotting it tangential to a particular line, let's say we plot curve C tangential to curve D, and we notice that this is rising, alright. But then, is it rising from left to right? This is more or less from right to right. So it's still facing the same side. So from right to right. So this does not qualify as an increasing function. So what is a decreasing function? So we are going to be having a decreasing function as something like this. I will draw a line that is tangential to it. So this line is tangential to it this way. So let's call this E, and let's call the line that is tangential to it F. Now, if we look at it from left to right, this line is decreasing. So this line that is tangential to a particular curve, from left to right, is decreasing. So this is an example of a decreasing function. So there is a way the use of differentiation is used, is made use of in order to tell if a function is increasing or decreasing from the first derivative and all of that. So that is not what we are really going into. Number 2 is about concavity and convexity. So now we want to know if our curve is concave, we want to know if our curve is convex. So calculus also makes derivatives also make us aware if our curves are concave or convex. Now, there was this funny example that I used to use before this particular period, but then with more understanding, with more light on the matter, I think it is better explained this way. So when you have your line, when you have your curve, above the line, above a tangent, Okay, when you have your curve above its tangent, so let's say you draw a line tangential to it, and then you have your curve above that tangent. So above that tangent, we see that that curve is convex. The curve is convex. I think that is just the easiest way to just have an understanding of what concave and convex means. Now, when you have your curve below its tangent, below it, this is, we are plotting this line. This is a line that we are plotting tangential to this particular curve, or let's say this curve is tangential to this particular line. Anyhow, so look at this curve now. So when you have this curve, below its tangent, we say that it is concave. So when it is above its tangent, it is convex, and when it is below its tangent, it is concave. Now let us talk about these two lines. This is an indifference. Oh, I've written the answer. So how do we prove that this is convex, and how do we prove that this is concave? So all we just have to do is to draw a line tangential to this. This looks like an indifference curve. So when we plot a line tangential to it, so make sure that it doesn't enter it. Alright. Now we then realize that our curve is above the tangent that we just drew. Alright, and because of that, our curve is convex. Now, how about this that looks like a backward bending labor supply curve? And let us draw our tangent. Of course, the tangent cannot be inside. No, we are not trying to draw a chord or whatever it is. Alright, so this is going to be the tangent. Apologies for my drawing. No, something like this. Alright. Something like this. And then if you look at it, this line then happens to be below, that is inside its tangent, and because of that it is concave. So when it is below the tangent, it is concave. Look at here, it is inside this, it is concave. Look at here, it is inside the tangent, so it is concave. Here it is outside, it's above its tangent, it's convex, and then here it is above its tangent, so it's convex. So that is the reason why one of the properties of an indifference curve is that it is tangential to the origin. Now this is the origin, so it is backing the origin, tangential to the origin. So there is also a way that differentiation helps us to know that derivative also helps us to know that our curve is concave or it is convex. So we won't talk about that, we won't go into that now. So when we get to number 3 and number 4, so we will shed more light on that. Now number 3, we have relative extrema. And what does relative extrema mean? So let me come from a relative extremum. A relative extremum is a point at which a function is a relative minimum or maximum. All of these things, they look like big grammar. Alright, a relative extremum is a point at which a function, so all of these curves now, they represent a function. So you are trying to plot y as a function of x. So by the time you start plotting the points together, and then you draw a line, and the line matches all or most of the points, we then have a curve of, let's say, a straight line if the function were linear. So here, a relative extremum is a point at which a function is a relative minimum or maximum. So you are just trying to know if a function is at its, if a function is expressing a lowest point, or if a function is expressing a highest point. Now something like that. So if it's expressing the lowest point, okay, so we call that a relative minimum, or a highest point, we call that a relative maximum. Now the way to identify a relative maximum or minimum is first to understand something that we call a relative plateau or plateau. I don't know, Plateau. Alright, so you need to have that, and that is just relative plateau is a point where your function is neither increasing nor decreasing. So at that point, the slope of your function is 0 or undefined. Now the slope of your function is 0 or undefined. Now I will show you an example of relative plateau here. This here is an example of a relative plateau. If you take the slope at this particular point, the slope is divide the x, right? Since we have x and we have y here, so divide the x is going to give us 0. Do you know why? Now we have, let's say this is x1, and let's say this is x2, for example. Alright, and the slope is changing y as a result of the change in x, right? Now let us look at it. There's going to be a change in x, definitely. So if I move from this point to this point, for example, or I move from this point to this point, for example, there's going to be a change in x, definitely. But then this is only intersecting one point on the y-axis. Alright, so when it was x1, it was y1. Now it's still y1 and then we have x2. So there is a change in x1, but there is no change in y. Now that simply means that if we are, where can I write that? So if we have a change, we don't have a change in y, but we have this, we have we don't have a change in y, that is 0, but then we add, we have a change in x, which is like positive. And let me just write change in y. So this is 0, and this, let's say, plus 5, for example. Now 0 divided by this is 0. Alright, so the other way around as well, if we have a change in y and we don't have a change in x, that's going to be undefined. Now if we look at this particular slope, what we're talking about increasing functions, let's say we were to plot this, something like this. Okay, I'm not using this anymore. It's something like this. Now if you check this point, this is y1, this is x1. Now it is still like here, this is y2, and then this is x2. So by the time you do change in y, the y, by the time you do your divide the x, what you are going to be getting is positive. So this is, I guess we are having a positive slope. But in this particular case, what we'll be having is 0. And if it were the other way around, I guess if you have something like a straight line like this, and probably have something like let me plot it very well, something like this, and then so on the y-axis we'll be having y1, okay, x1, and then we'll still be having y2 and x1. So y will be changing, x isn't changing. So our change in y will be positive, let's say plus 7, or change in x will be 0. Alright. And this is going to give us undefined. Alright, undefined. So I guess that is what that is talking about. So for us to know if a function were exhibiting a relative maximum or a relative minimum, we need to be at the point, we need to be on a plateau, on a relative plateau. So where the slope, divided by x is 0 or undefined. Now, let's move to the next one. For optimization of function, this is what economics is basically concerned with, optimization of functions, and this is just trying to tell us if a function, this is just a way of deriving relative maximum of a function and a relative minimum of a function without the use of a graph. So that is optimized, and this is what the bulk of economics is all about, especially microeconomics. This is we're talking about optimization of maximization of revenue. Of course, revenue is a good thing. So in economics, what is good you maximize it, what is bad or what is not good you minimize it. So cost is meant to be minimized. Cost. So when we minimize cost, we are trying to look for a lowest point. Alright, lowest point on the cost function. So we are trying to maximize revenue. We are trying to look at the highest point. So and that highest point is not just highest point. We are talking about an efficient point, because a point may be there may be a better point. Okay, don't let me go into theory. Don't let me go into the theory of things. So let's just okay. What I'm trying to say is there's a quantity that a supplier or a producer can produce, or let me say sell. I can sell that will yield the maximum profit possible. So it is that maximum profit that is being looked out for, or maximum revenue possible. Now beyond or below that quantity, let's talk about profits, for example. Profit is meant to be maximized because it's a good thing. Now there is a point where there is a certain amount of quantity that will give you the highest profit possible. Now if you produce above that quantity thinking that you should be generating more revenue, you would end up as a producer incurring more costs than revenue. In fact, you may be incurring more revenue, alright, but then you'll be incurring cost that is greater than the increment in revenue. So by the time you now take the net of it, total revenue minus total cost, your profit will be smaller than if you had been on that point where your profit was maximized. Now we'll talk about that later on. So optimization of functions. Now there are things that I really want us to understand. I guess I just have to clean this board and show us something. So to get if a function were being maximized or minimized, that is, we are trying to look for the relative minimum or relative maximum. I was talking about relative plateau. So as since I've already established that when you're talking about relative plateau, the slope at that point is 0. So we are coming. So I'm not plotting any curve yet. I'm just assuming that there is an invisible curve. Okay, we are talking about a function whose that has a relative plateau. Alright, that has a relative. Now I want to tell, is that function being maximized or minimized? That is, does that function have a relative maximum point or a relative minimum point? So what we just have to do, we call them relative because a curve could exhibit a curve could have a minimum, maximum, whatever like that, and it could be in form of a wavelength. So one relative to the other, this relative to the other, and something like that. So that's why it's relative. But these are quadratic functions. No, these are quadratic. Exactly, these are quadratic functions. So you get to have a minimum point or a maximum point. When we start talking about polynomials and whatever, we'll be having more than a maximum or minimum and all of that. So in this case, we now want to, how do we know if this function is exhibiting a relative minimum point or a relative maximum point? Now there are steps. Now if you were given a function, which is what we'll be talking about in the next video, what you have to do is to find the y, the x of the point, that is, find the first derivative. So you find the first derivative of the point, then you equate it to 0. Now equating it to 0 is like you are already assuming. Equating it to 0 is just saying that you are establishing that that function has a relative plateau. Alright, but that doesn't tell us if this function is a relative minimum or a relative maximum, and that is why you have to play the second derivative. If you recall from the very first video, second video on calculus on differentiation, I was saying that there are times when you have to differentiate a function more than once. So sometimes once, twice, 3 times, 4 times. I didn't go into that because I had this particular parts in mind. Okay, so we are just going to find the first derivative of a function and then the second derivative. Now in your classes, in your exams and all of that, your lecturer or your teacher could ask you to find more than the second derivative. It's not a very difficult process. So now you set the first derivative equal to 0, then you will get values. Now the values that you are going to get are called critical values. Alright, they are called critical values. So maybe you just want to note that they are called critical values. Now the next thing is you then find the second derivative of that function. We are going to do that in the next video, so just watch out for that. You find the second derivative. So when you find the second derivative, if the second derivative happens to be positive, if it happens, that is the first derivative is talking about the first slope. Now that is equal to 0. That's telling you that okay, this is a relative plateau. And second derivative is telling you about the next slope after that first slope. Now if that next slope were positive, okay, if it happens to be positive, that simply means that after this point, you don't know where your graph, you don't know where the function is coming from. So after this point, a positive slope simply means something like this. Okay. Something like this. So this is just trying to tell us that this point for this particular graph is a okay. Let me put it. So it's just saying that we have something like this. Okay, is that properly plotted? Alright, so this is just trying to tell us that we've assumed that this relative we've assumed that this is a relative plateau, right? Where there is where the slope is already 0. So if you get positive value for the next one, so it simply means that our graph is now upward sloping. Okay, and what this simply means is that the graph was coming from a point like this. The graph was coming from a point like this initially. Alright, and that tells us that okay, what we have for this particular graph is a relative minimum point. It's a relative minimum point. So when your second derivative happens to be positive, so that means you are already going above, you're already going above the tangent. Alright, you're already going above the tangent. So that is just telling us that the function is exhibiting a minimum point or a relative minimum. Now the second one is this. So you set your function equal to 0. So when you take the derivative, if that's equal to 0, you get your critical values. Now you find the second derivative of that function. So when you find the second derivative of that function and it is negative, so here what we have here is the y squared. No, what we have here is the squared y over the x squared. Okay, which is positive. The squared y over the x squared is positive. The y dx is this, so this second derivative. And if it were expressed in terms of f, so f of x a 0, which is the same thing as this, and here this simply means that f is positive. So here you have a minimum point. And okay, I forgot to add, and is this graph concave or convex? So this is telling us this graph is above its tangent. So if it's above its tangent, you have a convex, graph. So this is convex. This function is convex in nature, and it exhibits a relative minimum. Now we come to this. We set the y(dx) equals 0. We get some critical values. Now after that, what do? We find the second derivative, which is d squared y dx squared. Alright, so if it is negative, it's telling us that our graph is now downward sloping. That after it's passed through, after it's experienced that relative plateau, alright, where the slope is already 0, that the graph is now exhibiting a negative slope. So, and that simply means that our graph now is downward sloping. Alright, so the implication of this, or the meaning of this, is that this graph was coming from a point like this initially. Alright, so this kind of graph, this is what we have. So when your second derivative happens to be negative, then your graph, your function is exhibiting or is experiencing a relative maximum point. Alright, maximum point. So that is what it means. And then if you look at the graph, is this graph concave or convex? The graph is under its tangent, so it is a concave. The graph is concave. Alright, so it's a concave function, or whatever it is that you want to call it. So there is also a third scenario that will occur, which is when your second derivative happens to be 0. So if your second derivative happens to be 0, I think I'll be needing this now. Okay, so if your second derivative happens to be 0, so what would you be having? Now you have your first derivative as something like this. So your first derivative is already 0. Now you don't know the nature of this graph. So is it going to be upward sloping? Okay, is it going to be concave or convex? Is it expressing a minimum or maximum point at the end of the day? So when you do your second derivative and it is 0, so what it simply means that when it is 0 or it is undefined, alright, when you find your second derivative and it is 0 or undefined, what you have is an inflection point. So an inflection point simply meaning that your graph, your function or your graph is changing its slope. It's not just changing its slope, it's changing from being convex to concave, or it is changing from being concave to convex. Now, and in that case, the tangent is going to pass through that line. So you'll be having something like this. So you're having something like this, then which is now going this way again. So this is what you are going to have. So we call this something like, so which is, I think this is an example of your total cost curve, and something like this. So what is acting as, what should have acted as a maximum for this portion of the graph is acting as a minimum for the portion of the other graph, right? And it could be downward sloping. So it could be, let's say you have this, it could be something like this, changing from, you put your tangent, changing from being convex to being concave. Alright, so, and this occurs when your second derivative is 0 or it is undefined. So when you have second derivative being 0 or undefined, you cannot tell if the graph is concave or convex within the framework of what we are doing in this place. And your second derivative is going to be 0 or undefined. So that's that about this particular class. That's a wrap. If you enjoyed the class, please click on the like button. Make sure you leave your comments behind. Click on the subscribe button as well. You see a notification bell that it's going to come up after that. Click on the bell. Subscription is totally free. And share this class with your friends, your colleagues, and everyone in your class. So I'll wait the next class where we shall be talking about calculations. That makes things easier. Okay, because just await the class and see what we're going to do. Thank you very much. See you next time. Hope you enjoyed the video you just saw. If you want more of our videos, please make sure you subscribe to the channel and click on the notification bell. Now, there is a way to enjoy to make the best of our YouTube channel, which is to go to the playlist section of every video or of every topic. So what you have to do is just type Emoji Economics on YouTube when the page displays, make sure you subscribe. A bell button appears immediately, so you click on that bell button. Then go to the playlist section. So you're going to see videos, playlists, description, and all of that. So just go to the playlist section, and whatever topic you are looking for, look for the playlist and click on the video. Now our playlists have the classes arranged in a very chronological manner. So if you want to see a class on ISLM, so it starts from the beginning, the simple ones to the difficult to the complex ones. So if you want to see a video on, let's say, elasticity of demand, so you start from what is price elasticity, so from there then to the basic ones, and on and on. So I'm just telling you that in case you really want to make the best of this YouTube channel. And there's also one thing that I want to add, which is that our YouTube classes may not be enough for you. You may want a regular interaction with the tutors and all of that. So what you just have to do is to check the description of the video. You are going to find a WhatsApp link. So but before you do that, I really have to tell you that clicking that link is going to lead you to one of our schools. It's going to lead to some of our schools. So we have MOG School of Economics on WhatsApp, and we make use of our YouTube channel to run the groups. So the classes are paid for, so you're meant to pay for them. So to join our econometry school, so that is 2,500 naira per month, and to join our microeconomics or macroeconomics schools, so that is 2,000 naira per month. We also have we don't have classes, or we don't have schools of mathematical economics, because microeconomics has its mathematical aspects as well as macroeconomics. So those mathematical economics aspects of the two economics. So the mathematical aspects of macroeconomics and microeconomics are treated together in this. So the mathematical aspect of macroeconomics is treated in the macroeconomics school, and the mathematical aspect of microeconomics is treated with the microeconomics school as well. So I'll see you next time. Thank you very much for watching. So the mathematical aspect of macroeconomics is treated in the macroeconomics school, and the mathematical aspect of microeconomics is treated with the microeconomics school as well. So I'll see you next time. Thank you very much for watching.